One of the best things about physics is we can use it to accurately describe different things and their motion. So let's imagine we've got a car and we plot its distance over time on a distance time graph. Now, if its distance goes up in equal intervals along with time, we say it's traveling at a constant speed. Speed is distance divided by time, meaning that is constant. If we then plot it as going horizontally, that indicates the car or the object is now stationary because its distance is not increasing. If we plot it coming back down towards the x-axis, that is another constant speed because it's the same straight line, but is in the opposite direction because it's going downwards. It's also steeper than the original line, the line in red, so steeper gradient indicates it's going faster or at a higher speed. Now, technically, I've drawn this as a distance time graph. We should really draw it as a displacement time graph. Displacement means it's the same thing as distance, but it's got a direction. So it's the shortest distance between 2 points. So meaning if you start off in one place, end up at that place, the displacement is 0. Let me just move this down so you can see. So that's distance time graphs. Let's have a look at a velocity time graph. So it's another way of representing motion. This time our y-axis is velocity. You've got to be able to spot that in an exam because it describes a different journey. So this time, if the velocity is increasing gradually, it's not a constant speed. The change in velocity divided by the time is equal to the acceleration. So acceleration meaning the car is speeding up if the velocity is increasing. So we say this is going a constant acceleration or linear acceleration. If we draw the line going horizontally, that's not stationary. It's now going at a constant velocity, meaning the velocity isn't changing, but it hasn't stopped yet. If now we draw the line going back down to the x-axis, that indicates that there is a constant deceleration. Decelerating means slowing down till it's going to be 0 velocity. Now it's a steeper gradient than initially. That indicates it's a higher acceleration. Don't say things like faster acceleration. It's a higher deceleration at this point. And the only point on the graph other than the start where it's stationary is where it reaches 0 again. Okay, so let's look at what else we can look at. Now, when we're describing these graphs, it's a good idea to describe the gradient, the rise over the run. It really helps us describe these different things. Let's have a look then at another velocity time graph, and this time I'm going to tell you what else you can work out from it. So another velocity time graph, similar sort of shape. They don't have to be these shapes, but we're going to stick with this shape for now. If I wanted to work out the distance or the displacement travelled, what I would have to do is instead of measuring the gradient, I would need to know the area of the graph. So the area between the graph and the x-axis. The reason for that is because distance equals velocity times time. And when you multiply two axes together, that represents the area underneath it. So let's break this up into shapes. We've got two triangles in either end, and I've got a rectangle in the middle. So I can work out the triangles by doing half base times height, and I can work out the area of the rectangle by working out base times height. Now, obviously, there'll be numbers on the graph you'll have to work out. So to generally speaking, you'd need to work out the number of boxes. If it's a curved line, you have to count the squares, which I know sounds ridiculous, but counting the squares and estimating how many there are is the best way of doing it at GCSE. Then you'd multiply by the value of one square. While we're talking about curved lines, if you want to find the gradient of a curved line, then you have to draw a tangent. So any curved line, don't just pretend it's a straight line. Draw a tangent at that point and work out the gradient of that tangent. One of the hardest things they can ask you about these graphs is curved lines. Okay, I'm going to draw another graph here, which is going to show you a specific example of a velocity time graph, which is so useful to know. This example we're going to talk about is about terminal velocity, which is a word you probably have heard, and it comes up a lot, but we need to be really specific in describing it. So the examples you might see are skydivers, cars, bikes, swimmers, lots of things that move in different fluids. So what happens first is for, let's say, the car as it moves along, it accelerates. Now, if you look at my previous video on forces, we will know that the car will accelerate because the forward force, or the engine force, or the thrust, you can call it, is bigger than air resistance. Air resistance is going to be very small initially. Now, initially, let's talk about like a story at the start. The engine force is going to be bigger than air resistance. Now, as the car or the swimmer or the skydiver speeds up, the air resistance increases. The faster you're going, the more the air resistance. If you cycle faster, there's more air resistance. So what we'd say then is that as you speed up or your speed increases, the air resistance also increases. And that's what causes the acceleration to decrease. So you see the line starts curving off there. It's less of an acceleration because it's a shallower gradient. Stage 3, which is the part where it goes horizontally, as we've just talked about on the bottom left graph, is a constant velocity. Now you need to be able to link this together with the forces. The reason it's a constant velocity is because the engine force, in this case for our car, is equal to air resistance. Therefore, there's no resultant force, so there's no acceleration. F equals m times a, no force, no acceleration. That could be a 6-mark question or a 4-mark question in your GCSE. Comes up a lot. Last thing we're going to talk about when we're talking about motion, this is for combined or separate science, is stopping distances. So stopping distance for a car is made up of 2 parts. It's made up of the thinking distance and it's made up of the braking distance, which I spelled incorrectly there. Sorry about that. So braking distance, the things that affect that would be the tyre conditions, the road conditions, the weather conditions, the brake conditions, also the speed. Thinking distance is affected by someone's tiredness, whether they've used drugs or alcohol, things like distractions, mobile phones, and also the speed. Speed is in both categories, really important one to know. Now, how do we link those two things together? Well, a reaction time that is being increased because of drugs or alcohol is proportional to thinking distance. So the idea is that at constant speed, distance equals speed times time, so distance is proportional to time. Sometimes you have to mention that when explaining why reaction time affects affects the thinking distance. For braking distance, it's a little bit different. Distance is proportional to velocity squared. The reason for that is because of this equation here. So if I was to double the velocity, the distance would go up by a factor of 4. They are not directly proportional to each other.